It was about, in general, it's not about you memorizing this formula and do calculation quickly. And it's, if it is really the basic thing, it's all right, but that's not the point of it. So let's think about this problem again. This is a and b are constant, but it's not actually given, so it's algebraically it's a little bit cumbersome to do that, but I don't think it's too bad. So what was the idea? If you go through the integration by parts from experience, it seems like this looked like a times e to the ax cosine bx, right? That's involved. And b times e to the ax and sine bx seems like showing up again when you go through integration by parts repeatedly. Integrated, differentiate, integrated, differentiate. This is all you get, right? How many ever times you do it, and this is all you're going to get. Make sense? So we kind of assume, let's see if this is possible, if it is in that shape. And you figure out what this A and capital B are, right? So what did we do? We differentiate right-hand side and match with the left-hand side, right? So I'm going to write it like this. Derivative of left-hand side, right-hand side, correct? We did that. Select to leave this as an exercise. I want you to go ahead and be brave and handle those little a and little b and capital A and B as a constant and carry out the product rule. Is that right? Product rule here? Product of e to the ax times and cosine bx. Product rule applied 2 times, and then you will see this e to the ax and cosine e to the ax and sine shows up again, and you collect them, and then what's in front of it is just all constant. Okay? So apply product rule to the algebra and collect the same term, and you'll be able to go back to this again. Okay? So that's your work. So I underlined the red one, that's e to the ax cosine bx and e to the ax cosine bx. So I looked around, what's multiplied to that is capital A multiplied to A, right? That's e to the ax and cosine bx. So I wrote down here, A and multiplied by A. If you look at here, cosine e to the x cosine bx here, we have little b and multiplied to capital B, right? So altogether it's going to be little b multiplied. So if you collect them, it's going to look like that. The green one is e to the ax and sine bx. There's a negative b multiplied to a. So negative b times a. And e to the sine bx here, then little a multiplied to capital B. So I collected it here. That's it. Those are the 4 terms. So I differentiate the right-hand side. So it's supposed to be equal to which function? What's inside the integrand, right? That's the meaning of the antiderivative. So we want this thing to be e to the ax times the cosine bx. This is what we want, right? For that to happen, we have freedom of this choosing capital A and capital B such that this happens. So if you compare this one, okay, if that's 1 and if that's 0, then that's going to happen, right? So there's 2 conditions, and we have 2 unknown constants to choose A and B, capital A and capital B. So write that down. What we want is that A, little a given, capital A about to determine, this one has to be 1, and that one negative B, A, and positive AB. That one's got to go. That one is to be 0, right? So if you can solve this equation with A and B and capital A and capital B unknown, and that'll be the constant AB, you put it in there, and it does the integration by parts in a different way. Integration by parts is the reverse of the product rule. As you have seen, when there is a repeated integration by parts, usage is algebraically very cumbersome and difficult. And I find it, you better actually differentiate. That's a lot easier than going through integration by part multiple times. Just look at the target and just differentiate it if you know how it looks like. So how do you solve this equation? If it is this number, shouldn't find it easier to do that. But if it is like this, let's see. If I want to get rid of, for example, a b, then I will multiply a. So it's a squared a, ab, b, and that's a multiplied. If I multiply b there, this has the effect of the following. ab multiplied to 0 times 0. So that we have ab and ab shows up. It is the same coefficient. This one's b, and that one's a. then kind of think about least common multiple. But we don't know anything about A and B. It's just A and B. So this is one common multiple, not a least common multiple. If these are actually numbers, least common multiple will do a better job. You deal with the smaller size of the number, right? So why did I make these two things equal? So then when I subtract these two equations, they disappear and isolate A, right? So we do the same thing. So what do? I subtract the bottom row from the top row, right? And these two cancel. And you see that this happens, A squared A minus that bottom row is subtracted, right? So we subtract like this. And this is A, correct? So you collect an A in there. That's what that A is, a little a. Good? So it's equal to, what is it? Capital A is A over A squared plus B squared. Well, it looks complicated, but very neat and symmetric, like that. How about eliminating A? I'm going to multiply B there. I'm going to multiply A there, make that coefficient the same, and it's opposite sign. This time we're going to add. And nothing is going to happen. So I'm going to multiply B here. So it's ABA, and you see there's a B squared B equals B. Is that right? And if I multiply A down there, then AB shows up again, and A squared B, and it's still 0. Right? So we have the same AB. AB shows up in front of capital A. If you add this time these two, then this disappears, and these two becomes B squared and A squared, B, and right-hand side. It's just added together. It's just B. So if you solve for B, capital B, then very similar form with the B in the numerator. So we conclude not going through integration by part. It's very cumbersome, a lot harder than this algebra just went through, actually. So e to the ax was cosine bx. Is that right? Cosine bx dx is supposed to look like this. Some constant times e to the x cosine. Some constant e to the a sine bx. So capital A was little a. So the answer is a divided by a squared b squared. That was capital A, and e to the ax and cosine bx. And the second b was a b over a squared b squared. These are all constants. And then here's a function of pi to the x sine bx. This is the antiderivative of that function, which can be obtained by repeatedly using integration by parts. Okay? And there's a sine bx. It goes exactly like that, but that looks like a good homework problem. So I will leave that as a homework problem, right? That was not assigned. Good. So again, this is an example that I personally find it's better to just differentiate than in going through the integration by part. And you will see exactly this thing in differential equation. Some calculation goes through. I just went through. This happens in damped harmonic motion. This is the calculation you're going to go through in damped harmonic motion. All right? It is just, it's a spring mass system, and the damping from the air and the water, those things are calculated using these functions. And algebra and numbers that determines behavior of the system behaves like this complicated, right? Vibrations hard.